All right, so first we're going to go back. Oh, there we go. No one. Maybe. Here we go. Everything's connecting. There we go. Going to go back to a couple of chapter 1 problems. And these two were very commonly missed. So let's make sure that we are clear about what's expected here. Number 18 is an absolute value inequality where we're asked to solve the inequality and then graph on a number line. Now, a couple of you, the issue was you didn't graph when you got to this section because the directions to this section are on the previous page. And this is carryover from that section. So for a couple of you, that was the issue, was that you had not graphed your inequality for 18 or 19. Okay? But 18 had a bigger issue than that. So, tell me, what is the first thing we should do in order to try to solve this? Yes, sir.
You add 7 on both sides.
Okay, because if we're going to solve this absolute value, we have to get the absolute value expression isolated first before we can do the setting up two different inequalities and going from there. So if I add, let's do this in. If I add 7 to both sides first, then I'm left with the absolute value of 3x plus 1 less than or equal to what?
Negative 3.
Now what? Yeah.
There's no solution.
Why?
Because an absolute value can't be.
Yeah. Think about what you're actually saying with this statement right now. You're saying the absolute value of something, which represents distance, so it always has to be positive, is supposed to be less than or equal to something negative. Is that possible? Is it possible to make this statement true if we know absolute values always give us positive results, and this statement says make the absolute value less than or equal to a negative? Now, so right now, you can say no solution and be done with this. If you notice what your statement is actually trying to say. Now, many of you did not notice that, and so you went ahead and went through the work and you got answers. So why did you get answers if the answer is supposed to be no solution? How does that make any sense? That some of you actually thought you got solutions when the answer is no solution?
Because when we divided it up into two inequalities, we thought of 3x plus 1 as a positive number, like 3. Because when the absolute value of the sign is gone, then there is no reassurance that it will be a positive number.
Okay. So if you work this out and you split it up and you do your 3x plus 1 is supposed to be less than or equal to negative 3, and then we know we're supposed to set up the opposite, so 3x plus 1 is going to be greater than or equal to positive 3, and you work it all out and you get your answers. If it looks like we have solutions, then how are you supposed to know that we don't have solutions? Exactly. Those of you who left those crazy fraction answers as your solutions didn't check them. If you put them back into this inequality that we started with, this original inequality, You cannot get your solutions to actually work. Okay? So again, I cannot stress this to you enough. When you are especially dealing with problems where you are supposed to solve an equation or an inequality, you have got to get into the habit of taking an extra 10 seconds and just mentally, doesn't have to be on paper, but just mentally stick your solutions back into your equations and make sure they actually are a solution, that they actually make your statement true. And what blows my mind, especially now that I'm teaching more upper level classes, like I get this from an Algebra 1 kid, okay? They don't understand yet. But Honors Algebra 2, Pre-Calc, I even see this in Pre-Calc, they'll actually do the check over on the side. They will have work that shows they got 2 different answers, and they'll still leave it. What? You just did work that shows the left side is not equal to the right side. Why are you saying you still have a solution? Okay, so 1, make sure you are checking. 2, check carefully. Make sure that your work is right. Okay, I can totally understand that if you get those different answers on either side that you would want to go back and just make sure all your arithmetic is correct. And 3, trust yourself. I think a lot of those situations are a case of, oh, well, I must have made a mistake and it's probably still okay, so I'm just going to leave it as a solution. No, you didn't make a mistake. Trust yourself. You're in Honors Algebra 2. You know what you're doing. Trust yourself that you know what you're doing. And if you get answers that don't match up, there's something wrong. Either check your work to make sure you did all the arithmetic right, or understand that this solution really isn't a solution. It doesn't really work. I can't use it. And if that happens with both of them, then I've got no solution. Which, if we go back to this statement, makes sense that there should be no solution, because my absolute value cannot be less than or equal to something negative. Okay? So be careful for those. Watch for those extraneous solutions. Once you get beyond linears, pretty much, just because it looks like you got a solution doesn't mean you actually did get a solution. You need to think of them more as potential solutions. Like if there is one, these are probably going to be it, but we're not guaranteeing these are it. You got to check them out. Okay? This one. You were asked to solve for t in an expression that says AT equals H minus BT. What is the difficulty in this one? What is it that trips us up in this one? Yes? There's t on both sides. So we're trying to isolate t, but we've got 2 t's. So that's what makes this one tricky. So what's the first step in trying to isolate t if we've got 2 of them? First step is to get them on the same side. Okay? So that means we're going to need to add the BT to both sides. So now I've got AT plus BT equal to H. Now, in first glance, that may not seem like you're moving toward isolating t because you just got more stuff over there with the 1 t that you had. But by getting t on the same side, what are you hoping is going to work out next? What can we do now that we have AT plus BT? Say again? Kind of. But since we're dealing with all variables, what's that going to look like? Yeah, so basically it's reverse distributive property, right? We're going to factor out the common t and rewrite it in the distributive property that looks like this. Right? Because both of our terms had the common factor of t in it, so we can factor out the common factor using the distributive property, sort of the backwards way. And so this is what we get next. So then how do I get t by itself? At least I'm down to 1t. That helped. So now what do I do to get t by itself? Yes?
You divide A plus B.
Yeah. So this is now two things being multiplied. And if this is the one I want to get by itself, then this is the thing that I need to divide by. So we're going to divide both sides by a plus b. And so we end up with t being equal to h over a plus b. Now for some of you, you had no idea. Like, there is actually kind of entertaining to see what some of you tried. For some of you, you were close, but somehow when you factored out t, this became a times b. You lost your plus sign. Okay? We're not losing any plus sign here. These two terms are still being added together, and we're going to divide by that entire expression to get t by itself. So don't lose that plus sign in something like that. Okay? All right, any other questions on those two? Just kind of wanted to go back and touch on those two since a lot of people missed them. Good with that? Makes sense now? Okay. Moving on. This one. This is not the one that's in your test. These are just some other examples, but it is similar to number 24. Now, in most cases, most of you answered the first part of this, which says, tell whether the data in the table shows a direct variation or not. And most of you understood that it did not. But, if not, explain why not. That's where we had a little trouble. Some of you had true statements, but they were not statements that necessarily explain why it's not a direct variation. Some of you had statements that explained why it was not a line, but a direct variation is more than just being a line. A direct variation is a special kind of line where we have to go through 0, 0, and so our equation always has to look like this. Now you can make it ax, you can make it mx, you can make it kx. The variable in front of x represents what we call a variable of, I just lost it. A constant of variation, there you go. A constant of variation. So it dictates by how much x is going to vary with y. Okay? What we don't have here is the plus b part. Because every direct variation line is supposed to go through 0, 0. Okay? So, when you have tables of values like this, what is the easiest way to tell whether you actually have a direct variation or not, and then explain why you do or why you don't? Okay? And it comes from taking this equation and rewriting it with a isolated. So in order to get a by itself, what would we need to do? Divide by x. So we can rewrite this equation as a is equal to y divided by x. So that's what you test. You test each combination of x and y. You take y divided by x, and you see if you get a constant of variation, meaning it has to be the same thing every time. If you do get the same thing every time, then you do have a direct variation, and you should be able to figure out what your equation is, because you now know A. But if you're not getting the same thing every time, then you do not have a direct variation. You may still have a line, that's possible, but it's not necessarily a direct variation line. Okay, so take a look at our first table here. What do I get from this ordered pair if I take y over x? A 5. What do I get from this ordered pair if I take y over x?
3.
A 3. How are things looking? Not good. Okay, I don't even have to test the other ones, because right now getting these two different a values already tells me this is not direct variation. Okay, now if you look at some of the reasons that you wrote, some folks said things like, well, the x is always going up by the same number, but the y goes up by different numbers. Okay, so the flip side of that is you're implying that in order to be a direct variation, x should go up by the same and y should always go up by the same. Is that happening here? Does x go up by the same number each time? Yes. Does y go up by the same number each time? Yes. Okay, so see why that's not a valid reason? What you're describing is what makes it a line. But it is a line that has a y-intercept. So it's not a direct variation line that's going through 0, 0. So the reason here, when we were to, excuse me, when we get to the step of explain why not, your why not is that your constant of variation, or your a value, is not the same. Every time I take y over x, I'm not getting the same answer. So that is why it's not a constant or a direct variation. Because your constant of variation is not the same. It's not constant. Yeah.
So that pairing or table, it's still a linear equation, but it just doesn't show the variation.
Correct. Yep. And in most cases, that was the problem in that problem, was that your description was describing a line, but not a direct variation line. Yes?
So if we see this on the test, do you want us to write what A equals under, or can we just write A is not equivalent?
I would want to see something that shows me that your A's were different. Yeah, so it's usually something that simple is just under each ordered pair if you have a table like this. So under each pair of x, y's, if you just write, well, A in this case would be this, and A in this case would be this, and as soon as you start seeing they're different, then you can just make your statement that, okay, so the A's aren't all the same. Okay? How about the second one? Raise your hand if you think it is a direct variation. Raise your hand if you think it is not. Katrina, why do you think it is not?
Because whenever you do the y over x, it's not the same.
Okay, so if we just start here with the first one, what's my y over x going to be?
12 over 5.
12 over 5. Can't really simplify that. But then what's my second one going to be? What? Come on, baby. There it is. 1, 2, 3 over 10. Can that be simplified? No. So is that going to be equal to that? No. So we're in that same boat. Our A's are not going to be the same, so this is not going to be a direct variation. How about the last one? Raise your hand if you think it is direct variation. Raise your hand if you think it is not. Okay, so what is my A here?
2 over 3.
2 over 3. What's my A here? 4 over 6, but what does that reduce to?
2 over 3.
Bingo! Okay, now, just because 2 of them match doesn't mean they all do. That's kind of what you saw in your pre-test, right? The first 2 ordered pairs actually did give you the same answer, but then it was the third and the fourth one that went horribly awry. So you have to check them all to make sure. Okay, so what's our third set here? 6 over 9, what's that simplified to? Awesome! And our last one? 8 over 12, which simplifies to? Bingo. All of the A's are the same. So then what would the equation be that relates x to y? Exactly. Because you just found A, right? You found it 4 times. So all you have to do now is go back to this general form for direct variation, substitute the A for whatever you found for A, and there's your equation. Okay, so that's what you would give if you actually do get direct variation. If you don't get direct variation, it should be for this kind of reason. Questions? All right, next. More absolute value, but what's different about these absolute value equations as opposed to the chapter 1 absolute value equations? Didn't you have to graph the other ones? Oh, well, equations not so much. How about equations and inequalities, if we talk about them together? What's different about these as compared to the ones we saw in chapter 1? These have 2 variables. Okay, so when you see the equations and inequalities like you did in 15 and 18 that we talked about just a minute ago, and 19, those are all absolute value equations and inequalities that only have 1 variable in them. And so once you've solved them out, you're asked to graph them, but you're graphing on a number line because you're only graphing 1 variable. Now we're looking at absolute value equations and inequalities in just a minute, where we have 2 variables. So that means we have to graph on a coordinate plane because we need an axis for each variable, so we need 2 axes. Okay? So, when we talk about absolute values, does anyone know what the absolute value graph looks like in general when we've got 2 variable absolute value equations? Amy, do you know? Yeah, it's a V shape. It's very similar to quadratics. Okay, there's a lot about absolute value graphs that are very similar to quadratic graphs. But the thing is, a quadratic is very rounded because you get that U-shaped parabola, whereas an absolute value is very straight, and you get a V rather than a U. Okay, but there are a lot of similarities, such as absolute values have vertices. The vertex is going to happen where that corner is. okay, where the point of your V is. Absolute values can open up or down, just like a parabola can. And what determines whether a parabola opens up or down? Negative or positive what? A, right? So it's that first coefficient on x squared. If that's positive, we're going to open up. If it's negative, we're going to open down. Same thing with absolute value. The A in this case is a number that's out in front. I don't remember if we did this in Algebra 1 or not. Do you remember vertex form in Algebra 1? Any of you remember vertex form? So we've got the standard form for quadratics, which is this. Sorry. Let's try that again. Ax squared plus bx plus c, right? That's the standard form. That's probably what most of you saw in Algebra 1. But then quadratics can also take on something that's called the vertex form. And the vertex form looks like this. Does that look familiar to anybody? A couple of people maybe have seen that. Well, if we look at the general form for absolute value, it looks very similar. So that A value is the one that's kind of out in front that we're going to multiply by. And then inside, we have x, but we could subtract some number from it, which is an h value. And then on the outside at the end, we have another number we could add or subtract, which is k. Okay? The a, the h, and the k represent what we call transformations. So each of those numbers has a certain effect on what our graph is going to look like. So most of the time, if I'm just talking about the parent function, the very simplest form of the absolute value function, which is just y equals absolute value of x, then what would it look like? Well, if I put in 0 for x, what do I get for y? 0. Okay? If I put in 1 for x, what do I get for y? 1. 2 for x? 2. 3 for x? 3. So it's very easy right now to go, oh, it's just a line. But what happens if I put -1 in for x? We get 1, not -1. So it's not just a line. If it was just a line, they would have written a linear. Okay? So the fact that they're writing an absolute value equation or inequality means this is something different. And if I put in -2, we get 2. If I put in -3, we get 3. And so now you're starting to see this V shape. So that's what we call the parent function. It's the simplest graph and the simplest function of absolute value of x that we can have. And this is what it looks like. Now, when we have a, h, and k values, they affect what this graph is going to look like. Okay? So if I have an a value out in front is going to cause, there's two possibilities actually. If a is negative, just like we mentioned a minute ago, then it's going to open down instead of opening up. And that actually is a reflection through x-axis. Okay, so having a negative a is going to cause it to open down instead of opening up. Excuse me. If we have an a that is something other than 1, then that's going to cause what we would call a stretch or a shrink. Now, if you think about this, if you have, I can finally use it. All right, so if I have something like this, right? If I want to do a vertical stretch, then it would be like taking a hold of the top and a hold of the bottom and start stretching it. Now when I do that, what happens to the width of it? It gets skinnier, it shrinks, okay? But vertically we're stretching. So when I do a vertical stretch, what looks like is happening is that my graph is going to get skinnier. Okay? If, on the other hand, I do a shrink, or sometimes called a compression, okay, then that means I'm taking hands on the top and the bottom, and I'm going to squish. But what happens to the width as I squish? It gets wider. So a vertical shrink or vertical compression causes my graph to get wider. Now, we're going to talk a lot more about what A's do and when it stretches and when it shrinks and what that looks like and all of that. For right now, with absolute values, the trick is whatever your A is the slope of your right branch. Okay, let me say that again. This part of our graph, the right side, the slope of that will equal whatever A is. Okay, and then this side will simply be the opposite of A. Now, if you don't remember that, the other thing you can do is just once you figure out where the vertex is, put in a couple points to the right and a couple points to the left and work it out and get answers if you don't remember this. But if you can remember this, then this becomes pretty easy because once you decide where the vertex is, then the right side you just follow whatever A is for slope, and for the left side you just reflect it or make it the negative A for slope, and boom, you got a V. Absolute value. You're done. Yeah.
And so like for the first one, what would the plus 1 be? Is that the y-intercept?
Okay, so this is all A. So this would be if we had a number out here in front. Okay, right now it's 1. Exactly. Then we have these other numbers that get added or subtracted. So A gets multiplied out in front. H and K get added and subtracted. H causes our graph to do a horizontal shift. H, horizontal. You know it took me till last year to figure that out. There are days where I wonder why I'm a math teacher. I've been teaching math for 27 years. Took math for 4 years in college. Took math through high school. Last year was the first time I went, oh my gosh, H, horizontal. Anyway, H is a horizontal shift. Moves things left or right. K makes a vertical shift. Moves things up or down. Okay? Now, the tricky part of this is the general form when we have A, H, and K in there has minus in front of the H. So you have to be careful because when I write something like x minus 2, what is my actual H value? 2, not negative 2. Right? It's easy to think, oh, it's minus 2. The negative's there. We're always supposed to include the minus as a negative. Well, not now. Because the minus was part of the original form. So in order to end up with an x minus 2, H must have just been 2. Okay, so my h value here is a 2. What's my k value? That's the 1, because that's what gets added or subtracted on the outside. So h is added or subtracted on the inside, k is added or subtracted on the outside. And because it's a plus 1, luckily k is what it looks like. There's no trick to k, it's just h. So, with absolute values, what happens is my vertex here always happens at the ordered point h comma k. Because the parent always starts at 0, 0. So if I move horizontally to the right because of a positive h, I'm going to move however far h told me to. And then k is going to tell me to move up or down, and I'm going to move however far k told me to, and I'm going to end up at the point h comma k. Okay? All right, so let's actually do this for this orange one. I'll even switch to orange just for fun. Oh, come on. How do I get you to go away again? There we go. All right, so we said h was 2. We said k was 1. So where's my vertex going to be? 2 comma 1. 2 comma 1, right there. What is my right-hand slope going to be? A, which is 1 in this case. If nothing's there, we assume it's just 1. So my slope doesn't change in comparison to the parent I started out with. And that means my left-hand slope is -1. So in terms of width, my V looks just like the parent did. The only thing that changed is the position of it. I slid it over 2 to the right and up 1 because of that h and that k. That's what this graph looks like. Make sense? Okay, so what about this one? Let's go green. Here's how I would recommend that you do these problems. Start by identifying what's my A, what's my H, what's my K. Pick those numbers out of your equation or your inequality first, and then you'll know what you're working with. So what's my A value this time? -2. What's my H value? Good. Paid attention. What's my K value? 3. Why is this -1 if it says +1 here?
Double negatives positive.
Right. So the only way I'm going to get an x plus 1 is if it was x minus -1 and h was -1. Okay? All right, so where's the vertex?
-1 comma 3.
-1 comma 3. -1 comma 3. Oh, lost it. Come back. Come back. Oh, why does it keep doing that? I'll do this one more time. Here we go. Anyway, it's there. You see it? It's really small, right there. Okay, there's -1 comma 3. What is the right side slope? -2. Which means, which way is my V going to open this time? Down, because A is negative, right? So a -2 is going to look something like, out of the shadow here, this. And then what's my left side slope going to be? +2, and just a reflection of what I had there. There, and 2/1 there, and 2/1 there. It's going to look something like this. Okay, so this -2 actually had 2 effects on this graph. One, it flipped it over so that my V opens down now instead of up. But the other thing it did was what? What else changed? Yeah, the slope got skinnier, right? So we've got that vertical stretch happening because my V got skinnier than what the normal black parent absolute value looks like. And those both were an effect of that A value. So A's kind of got a double whammy. It can cause reflection and it can cause stretch or shrink, depending on what the number is. All right, let's try this last one. Y equals 1/2 x minus 3. What's my A? 1/2. What's my H? 3. What's my K? 0. If there's nothing out there, then we assume we must have just been adding 0 and we didn't bother to write it. So where's my vertex?
3,
3, 0. Right about there. What's my right side slope? 1/2. That's going to do something like that. Left side slope? Negative 1/2. So just reflect it. So what effect did my A have this time? Stretched it horizontally, which means vertically it shrunk or compressed. Okay, Henry? Does that make sense? So that's how you get the actual V shape that you want for your absolute value, is by looking at those A, H, and K values. Okay? Now, what if we turn them into inequalities? Okay, so these are the same expressions that we had before, but they're inequalities now. So let me just go back here for a second. I'm going to trace this one so we don't have to redraw it for a second. Okay, then we're going to go back here, and I'm going to draw it with this orange so that it actually show up on the video when we get. You need to watch that. All right, so that's pretty much what our V looked like when it was an equation. Okay, but now we're saying that it's an inequality. We now are saying that y is greater than or equal to absolute value of x minus 2 plus 1, rather than being just equal to it. So think for a minute what you do with lines. Right? We've all done linear inequalities back in Algebra 1. What's the first thing you have to do when you're trying to graph a linear inequality with two variables? Think about the process. What's the very first thing we have to do?
You would graph it like another one, but if it's less than and greater, then it's a dotted line. And less than or equal to, or greater than or equal to, is like a solid line.
Okay, so there's kind of two steps there. The first thing is, where would it be if it was just an equation? Where does the line go? And then, when I go to draw it, should I be drawing it solid, because we had the or equal to in the inequality, or should I be drawing it dotted? Okay? Same thing happens here. The first thing you have to do is decide, where does the V go? So imagine that it's an equation, just like we did on the last screen. The V goes right here. But then when I go to draw it, should I be drawing it as solid or dotted? As solid. So leaving it solid is great. But now what's the last step? Shading. And how do we decide which side to shade on? By what? We can plug numbers in, so we can actually test a point in one region or the other. Anyone else have an idea? Plugging in 0, 0, so it's testing a point. 0, 0 is the easiest as long as it's not actually on your boundary line. Okay? Anyone else have an idea on how we can decide? Is that how most of you do it? Try a test point? Okay, so let's try 0, 0. What happens if I put in 0 for y and 0 for x? 0 minus 2, absolute value of that. 2 plus 1, is that greater than or equal to, or sorry, less? Is 0 greater than or equal to 3? No. So which side of the boundary should I be shading on? The inside of the V. Let's see. Do I have? Oh, I have a crayon. Let's do a crayon. That sounds fun. Aw, look at the crayon. Let's color. Okay, so that's the side I'm going to shade on because the 0, 0 point on the other side of that boundary didn't work. So it's just like the process for lines, it's just that our boundary is now a V shape rather than just a straight line. But the process isn't any different. Okay, make sense? All right, how about our green one? Let me just erase this for a sec. Okay, let's go back to my pen for a second. Pen. Let's go green. Okay, and then we'll go back to here since we already had it drawn. Where's my green? So green was right here. Pretty much. Okay. Okay, so if I go back here, I know position. When I go to retrace this now, should it be solid or dotted? Dotted. So this time, I'm going to draw the V but with a dotted line. Okay? Now, which side of that one should we shade on? Outside? Why? Okay, so if I put in 0 for y, oh, I got my crayon on. Can we do this with crayon? It's like, oh look, kindergartners can do this. 0 plus 1, absolute value of that, times negative 2, plus 3. 1. Is 0 less than 1? Yes, right? Okay. So, is 0, 0 on the inside or the outside of our V? The inside. So, that's the part we're going to shade. Looks like a Christmas tree. Yep.
For these like all these absolute value functions, what would change if in the absolute value we got like 2x instead of just x? What would the values be?
Okay, so we will actually talk a little bit more about what happens when you multiply by something inside when we get to actual transformation lessons. But the A on the outside does the vertical stretch or shrink. If you multiply by a B on the inside, it does a horizontal stretch or shrink, which kind of has the same effect, but works differently, and so we'll talk about that more when we get to the actual transformation lesson. But good question. No, that's good. Okay, makes sense? One more here. Our purple one. Let me erase this one again. Alright, come back here. Get our pen back. And we'll go back here and do our purple. There's purple. So purple looked like this when we drew the V. Okay, so when I draw this one, should it be solid or dotted? Solid, okay, so purple. Can just trace over this solid, no problem. Okay, excellent. And then which side of that one should we shape? The outside, because putting 0 in for y and x this time, 0 minus 3,
-3, which is
absolute value, times 1/2, 1.5, 3 halves. Is that bigger than or equal to 0?
Yes.
Yes. So now it's actually on the outside of the V that we want to shade. So go get my crayon. Oh, I'm feeling so stress-free. You know there's research now that says coloring is supposed to be a stress reducer, right? So kindergartners have it going on, right? That's why they're so carefree, because they get to color all day. All right? So it's not always on the inside of the V. Okay? A lot of times it is, but sometimes it's not. So you've got to make sure you're actually testing a point to see which side you're supposed to shade on. Make sense? Good? All right. Let's see. You know what? Take a quick break. Everybody stand up. All right. Put your arms up in the air. Really simple. Arms up in the air. I did this wrong the other day. Put your right hand on your left wrist and just pull. Stretch a little bit. Ooh. Oh, and you'll hear things pop and crack when you're 48 years old. And then just slowly come back up. And then put your left hand on your right wrist. Just pull over that way. Oh, it feels pretty good. And slowly come back up. All right. And then just lean over. Just kind of let it hang. Let your hips just kind of, your back just kind of, get intense and then come back up. Big breath in. Big breath out. Roll your shoulders just a little bit. And do one at a time. By December, we'll be doing dance moves. All right, have a seat. Okay. I want you to try these first. These are definitely Algebra 1 things. The absolute value things, I'll be honest, not surprised you didn't get those, most of you, because most of the time in Algebra 1 we don't cover them. And I know here at Concordia we don't usually cover them. Okay? So not surprised about absolute value stuff. I expected we were going to have to spend some time with that. This, however, is Algebra 1 stuff. And most of you did okay on the ones that were on the pretest, but we can always use a little bit of practice and a little bit of refresher to make sure we know what's going on. So I want you to try these 3 first, and then we'll see what you get. All right, let's see how you did. So, Sean, what's the first thing we need to do if we want to write an equation of a line that passes through the points 2, 5, and negative 1, 9?
Find the slope.
Find the slope. Okay, and what did you find for slope on this one?
Negative 4 over 3.
Negative 4 over 3. Everybody agree with that? Yes, remember, y's over x's. Rise over run. Okay, I did see on a couple of you that was the issue, was you put x's over y's and then that messed up your slope for you. Okay, so remember it's y's over x's. Okay, I have to start the names better here. Anna, tell me what I should do next.
And then I think you should plug in like one of the coordinates so you can find the y-intercept.
Okay, and what should I plug it into? My ear?
Oh, like so.
See what comes out the other end?
So now you have y is equal to negative 4 over 3x plus b.
Okay.
Plug into that to find b, and then you will have the slope and the y-intercept.
Okay, so Anna's suggesting that we plug it into this. Right, so we know the slope, we know the m right now. And then she's saying if I pick one of the points, does it matter which one, Anna?
No.
No. So I can pick whichever point I want because both of them are supposed to be on this line. So pick the one that looks easier. Now, you're going to find out throughout the year, I hate negatives. Like if I ever miss a problem, which I do, so don't be afraid to tell me when things look wrong. 9 times out of 10 it'll be because I'm messed up with a negative somewhere. Okay, and it's just because I get to going too fast and those little silly dash things are easy to lose. Okay, so if it's me, I'm going to choose to go with 2, 5. Because it's all positive, it's all nice and easy, I'm going with 2, 5. Maybe there's something about this that you're like, nah, I kind of like the negative 1, 9, we're going to go with that one. That's fine, you can use it, just be careful, don't lose your negative. Okay, so if I put 5 in for y, and I put 2 in for x, then I should be able to solve for b, correct? Okay, so this is going to be, what?
Negative 8 over 3.
Negative 8/3. And so I'm going to have to add that over here to the 5. So it's easier if I think about 5 as something over 3, so I have that common denominator to combine. So what's 5 as something over 3? So I'm going to end up with 15 over 3, and then I'm going to add over here the 8 over 3, which is going to end up being 23 over 3. Whoops. Ooh, 3 over 3, there we go, which is equal to my b. So am I done? Okay, and that is probably the most common mistake people make when they do it this way, is they get to that b, they go, yay, found it, move on. No, don't move on yet. Make sure you go back and actually write the equation. Y equals negative 4/3 x plus 23/3. Okay, then you're done. Then you can move on. Anybody find your equation a different way? Yeah.
I use point slope form.
Okay, what does that look like?
Take either one and do y minus. For example, when I use y 9, I did y minus 9 is equal to negative 4/3 times parentheses x plus 9.
Remember that form? Point slope form? Okay, so this can also be used. We're going to need to distribute here first. So we're gonna get negative 4/3 x and then minus 4/3. So then negative 4/3 times 1. And then, in order to get y by itself, we're going to need to add 9. But again, with these fractions, it's easier to think of it in terms of what is that over 3. So what is 9 as something over 3? 27. So I'm really going to add 27/3 to both sides. And I get y equals negative 4/3 x. Oh, forget my x there. There we go. What's that going to end up being? Plus 23/3. Did it change my answer to do it that way? No. As long as we're doing it correctly, we should get the same answer either way. Now, personally, based on the 27 years of experience that I mentioned a minute ago, I would recommend this way. Okay? Partly because it fits. Like, what do we have to work with? We've got points and we've got slope. What is this form? The point-slope form. Like, there are spots to just plug stuff in. And what you're working out from there actually is the equation. Whereas here, like I said, a lot of people sometimes get down to where they've solved for b and forget to go put it back into the equation. And so then they lose points because they're not completely right. I have also just noticed that most students, when they have missed this type of problem, have done it this way. Okay? And so it's not that I'm, like, if this is just really solid for you and you're good with this way, I'm not saying you can't. It's not wrong. Make sure you show me your work and it's fine. But if you're a little sketchy with this process, or you're still just not sure about the process at all and you're kind of figuring it out, I would recommend you do this one. Okay, but as you can see, you get the same answer either way, and as long as you're working carefully and you're confident about what you're doing, I'll take either way. Okay, goes back to what we said a couple days ago about there's not usually just one way of getting to things. This is one of those examples. Okay, so you have to kind of gauge for yourself what you're more comfortable with, what you're more likely to get the correct answer with. Okay, and then go with that method and make sure you're doing it well. All right, the green one. What do we have to do first on this one? Damien, what do you think we have to do first?
Put the y on one side and then put 2x and 6 on the other side.
Okay, so what would that give us? A negative 3y equal to a negative 2x plus 6? Okay, then what?
Then we divide each side with negative 3.
All right, so y is going to equal what?
2 over 3x minus 2.
Okay, why was it necessary to do that? Why does that help us?
Because if you want to know if the function is parallel to that graph, you have to know the slope.
Exactly. Okay, when we're being told things about parallel and perpendicular, and we're given an equation of a line that we're supposed to be parallel or perpendicular to, our first step is still to figure out slope. But instead of actually setting up the difference of y's over difference of x's, we instead look at the equation we're given and figure out the slope from the equation. This equation, however, was in standard form to start. So in order to get the slope, we're changing it into slope-intercept form so that we can now say, okay, so I know the slope of the equation, the line that I've been given, is 2/3. Now, what's the slope of my line going to be? 2/3, because parallel means we have same slope. So I'm going to be using a slope of 2/3 to figure out the equation for my line. Okay, and then from there, it's just like we did up here. Either using slope-intercept form or using our point slope form, we're going to use 2/3 for m. We're going to use the 1, 3 for our point, x and y, and we'll work it out to get our equation. So, Julian, what do you think the final equation should be in slope-intercept form?
Y equals 2/3 x, and then plus 2 1/3.
Okay. Put the brakes on. In equations, don't use mixed numbers. Okay, they're messy. They're confusing. They're gonna mess you up. Okay, so in an equation, just keep them in proper. We still want lowest terms. We want them reduced as much as they can be, but just keep them in proper. Okay, so 2 1/3 would be the same as what?
7/3.
7/3. That's how we want to write it. Okay? Everybody agree with that? What you got? Good. How about our last one with the perpendicular line? What's the first thing we need to do on this one? Emma?
Change convert the slope
To what?
to 1/4.
Okay, so from the equation we're being given, since we're already in slope-intercept form, we can see the slope of this line is -4. But then what's the slope that I'm going to be using for my line? The opposite reciprocal. Okay, remember slopes of perpendicular lines are completely turned around. Because we take the number and we flip it to make it the reciprocal, and we take whatever sign it had and make it the other one. So we always take opposite reciprocals for perpendicular lines. Okay? And so again, now we're back to slope and point. So we can go with slope-intercept form, we can go with point-slope form. What should be our final equation? Henry?
I had y equals 1/4 minus
1/4 minus?
plus ways. Oh, sorry, 1 for x.
Thank you.
Sorry.
Okay, minus what?
And minus add 4.5, which would be 9/2.
You agree? Is that what everybody got? Okay, so the moral of the story is, what do we always need in order to be able to write the equation of a line? A slope and a point. Sometimes we get more than enough, like when we get 2 points. Well, I only really needed 1, but I have to have the 2 to get the slope. Okay? Other times we have to get our slope in kind of creative ways from whatever equation's being given to us. Sometimes they just come right out and say, the slope is going to be this and it's going to go through this point. Oh, okay, easy. Boom, I got it. But always make sure you've got a slope and a point to deal with. And then once you do, you can choose your method for actually getting down to your equation. And unless it says otherwise in the directions, we're always going to be looking for a slope-intercept equation. So even when you start with point-slope, just manipulate it to get slope-intercept for a final answer. Okay? Good. All right. I think I have one last question here. How are we doing on time? Oh, actually, we're not going to do that one. Here's what I want you to do instead. In the last few minutes, I have got a 4-question little quiz exit slip here. 2 questions on the front, 2 questions on the back. I want you to do this the best you can in the last 7 minutes. Hand this in to me before you leave. And then your homework is posted on Canvas as to what you need to do for Friday, or what is today, Wednesday? Yes, so for Friday. Friday we're going to go through some Chapter 3 stuff, and then next week, Tuesday, will be our post-test. Okay? Yes? Yes, you can keep your pre-tests, study from them, go back over the ones you missed, rework them, see if you can figure them out. Especially after you go through some review problems from the book, it would be good to go back to your pre-test and see if you can figure out what kind of mistakes you make. You may keep your weakness. There you go.